Thank you. Jochen, thank you very much. It's a very generous introduction. I don't know if I can live up to all of that. But I'm very pleased to be able to talk here today. I've enjoyed many of the talks that you have sponsored, and it's a great opportunity. So thank you very much, and thank everyone for tuning in. Um, I will explain this title in a moment, but let me begin by just indicating what has maintained my interest in this subject, and it's really the connections to all sorts of different areas. One is artificial intelligence, obviously, but also psychology, as Joachim mentioned, how animals learn, how we learn. Uh, Connections to economics and finance, and certainly to neuroscience. There are connections to game theory. And then what played a large role in what we developed is control engineering and theory, operations research. So you'll see a little bit of that in this talk. So it was all these connections that has maintained my interest in this subject over the years. Now, I have to qualify things at the beginning. Now, I've been retired for almost 15 years. And this is not a cutting edge reinforcement learning talk because I have not been uh, participating to the extent that I used to. But I hope to convey the basic ideas and to mention a few of the new developments that are happening. Uh, and then a little bit of history, which is I think something that Sutton and I really delved into when we started working on this. So in terms of rediscovering reinforcement learning, if we go back to some of the very early days, Edward Thorndike studied various animals. Cats are mostly the ones mentioned, but he also did it with fish and so on, but created puzzle boxes and put the animal inside. And I think their food was outside, so they were motivated to get out. And they had some interesting latching mechanism that needed to be unhitched to open the door. And they would try lots of things and eventually stumble on something that would open the door. Then he would put them back in the puzzle box and they would release themselves more rapidly. And he'd keep doing this until eventually they would just immediately let themselves out of the box. And this became known as learning by trial and error. The animals are trying various things and finally stumbling on something that worked. More modern term is instrumental or operant conditioning. And he put forward this law of effect, and this was 1898. And here's a quotation from something a little bit later that describes the law of effect. And basically, of several responses made to the same situation, those which are followed or accompanied by satisfaction will be more firmly connected to the situation so that when it recurs, they will be more likely to recur. And those which are accompanied or closely followed by discomfort, the animal will, other things being equal, have their connections with that situation weakened. And that so that when it recurs, it will be less likely to occur. So this is a statement of one of many of the law of effect that Thorndike put forward. It's been heavily criticized and modified over the years, but this was the basic idea. And I just highlight here the fact that it's not just talking about finding something that works or that leads to satisfaction, but also connecting it to the situation in which that happened. So it's actually a connectionist scheme, not just a question of search. Um, so, and this was 1898. Trial and error learning, instrumental or operant conditioning are later terms for this idea. Now, Daniel Dennett, the philosopher, wrote a paper, wrote an article called Why the Law of Effect Will Not Go Away. And in fact, a quotation from it is that his claim is it's not just part of a possible explanation of behavior, but of any possible adequate explanation of behavior. Now, I'm not sure I'd go that far, but certainly the law of effect has not gone away, and it really underlies the basic idea of reinforcement learning. Now, to me, though, casting this into a more computational framework, I view this process as consisting of several pieces. One is control, that the animal is trying to influence future inputs. It's trying to control its environment to make it generate satisfactory inputs to the animal. It also involves search, trial and error, generate and test, variation and selection, depending on where you're coming from. Different terms are used, but it's a question of trying various things and getting an evaluation for them that indicates their value in terms of what the motivation is of the agent. And memory, in other words, this associative aspect. Remember what worked best in each situation, so you can start there the next time. You can pick up the search again when the situation recurs. So there's a generator and a tester, and they can both be intelligent. They don't have to be, the generator does not have to be random. And the evaluator needs to be smart in some sense. So now these are aspects that are not so much emphasized in people's work on reinforcement learning, but I think they're very important. One uses the term blind variation and selective retention. Blind doesn't mean that it's totally random or ignorant. It can be based on lots of information that has already been collected. Okay, now to machine learning, let me just mention that supervised learning, which is the most heavily used and well known, is learning from labeled examples. And it's an error correction process. So the examples say what the system's output should be, and then the actual output is compared with that to create an error. And supervised learning methods are error correction, or sometimes called learning with a teacher. So large language models, basically, the main component is to predict the next token, and that's done with supervised learning because the occurrence of the next token is the label for the preceding input to the system. Now, unsupervised learning is learning from unlabeled examples. The primary example is clustering, putting things together because they're similar and creating different clusters for different kinds of examples. Sometimes it's called learning without a teacher. Reinforcement learning, on the other hand, has been called learning with a critic instead of learning with a teacher. And the key thing to note here is that a critic does not need to know what the correct response or the correct output should be. You can still evaluate something without knowing what it should be. And this is a critical distinction that reinforcement learning takes advantage of. It's much easier to be a critic than it is to be a teacher in the sense of supervised learning. And this process has been called learning by trial and error. But actually, Sutton and I, in the early days of this, discovered that trial and error is not error correction, despite the fact that many people really thought of it as being the same. Trial and error involves the search process, not just a comparison with a given target. So something to keep in mind, that trial and error is not the same as error correction. Now, how did I get into this? I got a position as a postdoctoral fellow at the University of Massachusetts, and they were studying this idea that Harry Clough had. In fact, he was instrumental in getting them funded to study this. And he was a senior scientist with the Avionics Directorate of the Air Force Office of Scientific Research. And one book he had written earlier things was this book, The Hedonistic Neuron, A Theory of Memory, Learning, and Intelligence. His idea was that neurons are hedonists that work to maximize some local analog of pleasure while minimizing some local analog of pain, whatever that is. Um, now, um, this project at the University of Massachusetts that hired me as a postdoc was called Goal-Seeking Components for Adaptive Intelligence. So he was really interested in the idea that these hedonists interacted to create some form of intelligence. And that was what this project was designed to see if this made any sense. Was this a crazy idea? Had it been studied before? Uh, is it something that's worth pursuing? And that's what we were doing. So, whoops. Now, his specific hypothesis for how a neuron learns or adapts is when a neuron fires an action potential, all the synapses that were active in contributing to the action potential become eligible to undergo changes in their strength or efficacies. If an action is if action potential is followed within an appropriate time period by an increase in reward, the efficacies of all the eligible synapses increase or decrease in the case of punishment. So basically, he was saying that neurons implement a law of effect. And so that was the idea that we were charged with seeing if this was useful. What did it make any sense? Is it connected to any data that's available, and so on. Uh, so here's just a synapse showing a presynaptic terminal and a postsynaptic neuron, and the idea of eligibility uh, is something that is part of the presynaptic terminal, and it's a memory of certain conditions that set the synapse up for having a modification of its efficacy. Now, the principal investigators of this project at the University of Massachusetts were three. Michael Arbib, who is well known for many books that he wrote, and in fact, a small book he wrote called Brains, Machines, and Mathematics was something that I read as an undergraduate, and one of the things that got me interested in this field. Another PI was Bill Kilmer, who had worked with Warren McCulloch, who was famous for the McCulloch and Pitts paper that connected neural networks with logic computations. And so Kilmer was one of the authors of an early paper. The third person was Nico Spinelli, who was a physician and neuroscientist who was a part of this team. So I was able to work with these people, and fortunately, um, when Rich Sutton came as a graduate student at UMass, these PIs basically left us alone. they were happy with what we were doing, and so Rich and I really took over, and I thank all of them for being so generous with us. And of course, we benefited from them immensely by periodically talking to them, but basically they didn't tell us what to do. All right, now synaptic eligibility. There are lots of ways of implementing this, and what we did was assume some sort of temporal trace that gives the amount of eligibility over time since the action potential. And in fact, there were two kinds that we studied. One was contingent, which means that there was a confluence of a presynaptic and a postsynaptic activity shown in this picture, and it generates this bump that occurs over the future over hundreds of milliseconds, not just microseconds. So now another type would be a uncontingent type, and shown here is just a presynaptic input would generate eligibility without needing the postsynaptic activity. And so these two kinds of eligibility actually play a big role in what we did as follows. And in fact, we simplified it by not having bumps, but just an exponentially decaying trace, which kind of did some damage to what Clough was suggesting, but mathematically much easier to deal with. Now, in searching the literature for things that we thought were genuine reinforcement learning systems, we discovered stochastic learning automata, which in statistics are really known as multi-arm bandit problems. And Professor Narendra, who was at Yale, had authored many papers and edited several books. And the idea is that the learning automaton is trying to maximize some reward, and the environment generates rewards depending on the learning automaton's input to it, so that each action was worth a certain amount of reward, and the learning automata had to discover which was the best. And this is a lot of statistics and methods for doing this, but this was genuine reinforcement learning. And then I worked with a student then, Anandan. Here's a picture of him at the time. And we wrote a paper called Pattern Recognizing Stochastic Learning Automata. So by and large, the learning automata literature did not include the associative aspect. So we combined pattern classification, it was basically associative, with learning automata. And we wrote this paper called Pattern Recognizing Stochastic Learning Automata. And that's a key thing, is really these pattern recognizing learning automata were implementing a kind of law of effect. And there's Anandan today, who is still very active. Now, one thing we did at first, this was in the day when associative memory networks were quite popular by Cahonen and Jim Anderson, the idea of distributed storage of information. And you may have seen these pictures back then from the late 70s. And associative memories were information was stored by basically taking the outer product of a key and a response, and using that as an input, summing it to the contents of a matrix. Now, what we did was we decided to, I mean, we're influenced by all this. We thought that idea was really interesting, but it wasn't reinforcement learning. So we made a reinforcement learning associative memory. So the environment would not tell the system what the output should be. It wouldn't be supervised, but it would generate a reward, or labeled here as a payoff. And the units within this, what we called associative search network, were these pattern recognizing learning automata. And you can see here that we included noise in the activity of each of these artificial neurons, because that generated the search. They had to try things. And so we used a weighted sum, S, and then added noise to it. And that was the action of each of these neurons. And so this amounted to a team of associative reinforcement learning neuron-like units. And we published a paper of this, and not one of our most popular papers, but this was connecting to the excitement that people were feeling about associative memory networks at the time. Now, then later on, we expanded this, and we looked at the sequential decision problems. And in this case, it wasn't just an immediate payoff or an immediate reward, but rewards that accumulated over time, where the system would generate a sequence of actions leading to state changes in the environment, and possibly a reward at each time step. And this is, wait, oh, I can't read the bottom, but I think I say this is a Markov decision process. And so we adopted this framework as it's actually probably the simplest case of an optimal control problem. where you're really trying to generate actions at each state in order to maximize some long-term measure of reward. And one way of measuring it, often this is called the return, and this shows a return that is actually the sum, the discounted sum of future rewards. And it can go to some horizon or to infinity as shown here. And this discount rate can control whether it's short-sighted. If it's zero, it's just immediate reward. If it's near one, it's really accumulating over a long period of time. So this is a framework that has been adopted. It comes from other work, clearly, but we adopted this as a nice framework for looking at some of the issues that arose in reinforcement learning. Now, some key features of RL: the learner is not told what actions to take. It has to discover them. And it's variation and evaluation, which is a form of optimization. The rewards can possibly be delayed. And the issue of sacrificing short-term gains for longer-term gains arises in this framework. And there's a need to both explore and to exploit. Exploring is needed to discover what may be better, and exploiting is to utilize what's already known or assumed in order to gain reward. And we thought of this as considering a whole problem of a goal-directed agent interacting with an uncertain environment. Now, there have been lots of applications. Certainly board games, backgammon, Go, chess, poker, Stratego Go, video games, robots, energy management, self-driving cars, trading and financing, natural language processing, healthcare, for example, fine-tuning chemotherapy schedules that extend over long periods of time. And then there are applications in large language models, not the core fundamental part, but in various ways of improving their responses by evaluating responses, or in fact of allowing them to do a kind of reasoning, which is also a sequential decision task that succeeds in generating a proof or not. So it's an evaluation of a sequence of actions. So and I'm amazed to see RL being mentioned in lots and lots of things these days, not just this list. Then there's deep reinforcement learning. So it's reinforcement learning combined with deep neural networks. So of course, deep neural networks have been instrumental in generating, the surge of interest and activity with neural networks. Well, you can combine that with reinforcement learning as input to these pattern classifying learning automata. Now, a bit of history. So I gave a talk a while ago called "In the Beginning, Machine Learning Was Reinforcement Learning." And we discovered that this is true. This goes back to 1935. This was before computers existed. And there are many studies, this is just one, but electromechanical devices that were able to learn via what is essentially reinforcement learning. And this shows one by Stephen Smith, who was at the University of Washington. And, it's like a model railroad, and there are dead ends. And when there's a dead end, it backs up. I think this is what it does. And then the switch is set so it won't go in there again. And so it's doing a kind of an associative memory of the route that led to the goal. So 1935, and then Alan Turing in 48 suggested the idea of a pleasure-pain system. And he wrote this: when a configuration is reached for which the action is undetermined, a random choice for the missing data is made and the appropriate entry is made in the description tentatively and is applied. When a pain stimulus occurs, all tentative entries are canceled. And when a pleasure stimulus occurs, they're made permanent. So this is 1948. This was not implemented. There wasn't a computer at the time uh, that was available to him. But this is clearly a law of effect. In fact, it's very similar to the idea of eligibility, too. This idea of remembering something and then canceling it if things turn out to be different than what would be desired. But this was 1948. Yes. So and this was I think the earliest idea for implementing RL on a digital computer. And then Claude Shannon, famous for information theory, among other things, built another maze finding rat called Theseus and demonstrated it. And this was in the early 50s. Uh, Actually, what was doing the learning was the maze with relays, not the mouse or rat itself. So he was on television with this, and it was quite well known. But it's essentially kind of reinforcement learning because nothing's telling the robot or the rat which way to go. It tries things and sees what works. Now, an important paper is Farley and Clark, 1954, which was the first simulation of an artificial neural network on a digital computer. And this was reinforcement learning, actually. Uh, and in fact, they had 4K of 16-bit memory. And it was a randomly connected recurrent network with 64 stochastic linear threshold units. So very much like what we ended up studying. And it was trained with a reward signal that rewarded making one group of units have higher activations than another group of units. And they found that this worked. And this was artificial neural network doing reinforcement learning in the early 50s. May skip this, but it's basically the law of effect idea. Then their next paper, a year later, it's Clark and Farley. They used the same network, but they did supervised learning. And so this to us was kind of the demarcation when machine learning kind of switched from reinforcement learning to supervised learning. And in fact, whoops, I should have, yeah, so I was going to show a picture of, but I guess I took it out. The perceptron, which is well known for Rosenblatt, was supervised, not reinforcement learning. But Minsky's thesis in 54, he used units called stochastic neural analog reinforcement calculators. And these were like synapses, not whole neurons. And they were stochastic reinforcement learning systems that would change the weight based on the consequences. And he wrote a very paper that influenced Rich and I and other students who were working with us called Steps Toward Artificial Intelligence, published in 61. And he talks about credit assignment, which is a key problem, still an important problem. How do you get this training information to the right places and at the right times? And so this is a question, this is an issue, for example, that eligibility deals with to some extent. And then there are other mechanisms that have to face this problem. Arthur Samuel, a very well-known checkers player, back in the late 50s and mid 70s, was a reinforcement learning system that learned how to play checkers better than he could, better than Samuel could, and this was also reinforcement learning, and it would look ahead to hypothetical events. And he said, what we're really trying to do is to make a score for each position look like that calculated for the terminal board position of the chain of moves which most probably occurred during actual play. This was the basic learning mechanism of his checkers player. And this connects to optimal control and dynamic programming because it's a very similar kind of process to dynamic programming. And looking at this a little more carefully, dynamic programming is one method for estimating value functions. So a value function, a state value function, is a score for a state that really is a prediction of the return from that state. And then there's a fancier one that involves actions also, an action value function. And these are key to most reinforcement learning algorithms so that the return is the key thing that's to be optimized, not the immediate reward. And there are ways of estimating these through error correction. And for example, Rich Sutton's dissertation developed what's now called the temporal difference algorithm, or a class of algorithms. And the error, so this is error correction, not reinforcement learning, but the error is computed from any immediate reward signal, an estimate, the current estimate of the return, and then the old estimate of a return. So how much did this activity change the estimate of return? And this can be used in reinforcement learning systems because if this delta is positive, that's good. Whatever you did improved your estimate of future reward. And in fact, working through this under the right conditions, a TD algorithm will converge to, in this case, a sum of future rewards or any other signal. It doesn't have to be reward. Now, no discounting here, but that could be included very easily. So this algorithm has been playing a key role in algorithms and a lot of thinking about reinforcement learning. Now, we wanted to illustrate some of these things. And so we found this paper by Donald Mickey and Roger Chambers in 1968. And Mickey was the director of the University of Edinburgh's Department of Machine Intelligence and Perception. And so balancing an inverted pendulum by moving the cart back and forth is, it's a standard kind of control problem. And the way they tackled it, they divided the state space, which is the angle and the angular velocity, 2 dimensions, into boxes. They called the system boxes. And in each box, they said there was a daemon who would, when the box was entered by the state, would propose an action and then keep records of how long the system remained balanced or the pole remained balanced after that action was taken. So each box had one of these daemons, and it kind of worked. It wasn't a great algorithm, but we thought this would be really cool to try with an algorithm that we were fooling around with. And so we did a system that became known as the actor-critic system, which just had 2 of these adaptive neuron-like elements. One we called the associative search engine, associative search element, which is a law of effect type of element. And then the adaptive critic is a TD algorithm. And then its error became the reinforcement signal for the search element. And then we broke the state space up into boxes, just like Mickey and Chambers did. And this actually is our most widely read paper, 1983, neuron-like elements that can solve difficult learning control problems, 1983. And it actually, we had trouble getting it to work, but we finally got it to work. And in fact, we would now label these things differently. The AC, the critic, would be a TD reward predicting element. The search element would be the actor or the law of effect element. And then we'd call this reward. And this would be the TD error, which was the reinforcement signal. And so this became known as the actor-critic architecture. And another student who joined us early on was Chuck Anderson, who just retired as a professor at the University of Nebraska. And he did a system using a backprop, which had been proposed, which had come out by that time. Instead of breaking the state space up into boxes, he let this layered network create appropriate representations for this inverted pendulum problem. And so, um, so to me, this is kind of the first uh, application of deep reinforcement learning. Not very deep, but at least more than a single layer. Okay, now let's see the time. Yeah, so also these same ideas have been used by DeepMind in the AlphaGo and AlphaGo Zero systems that most of you have probably heard of, that learned through reinforcement learning to play very high level Go, which is a very challenging game. And basically AlphaGo Zero is the elaboration of AlphaGo 1, where they did not use any human developed strategies. The system learned from nothing through repeated play to do very high performing Go play. So then in a later DeepMind work, they did, as it says here, AI achieves silver medal standard solving international mathematical Olympiad problems. And so they actually created a system called Alpha Proof, and the outgoing part of it was basically Alpha Zero, and the 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 input part was a way of formulating problems in forms that the learning system could use in the reinforcement learning process. And so this another landmark, I think, from DeepMind, Google DeepMind, now at Google DeepMind. Okay. And okay, a little bit more time. All right, now let's look at the brain. This is about dopamine. So I wanted to touch base with this very interesting connection to the dopamine system. And so here's a sketch of the dopamine system in a mammalian brain or human brain, it looks like, but that dopamine comes from several different sites, but is broadcast widely throughout, in this case, the prefrontal cortex, and then another, the substantia nigra, is sending dopamine signals to the striatum. So this is connected to what we were doing because of work by Wolfram Schultz, who's a neuroscientist now at Cambridge in England. And it's been known for a long time that dopamine plays a role in how we feel pleasure and rewards. And so he wanted to figure out what these dopamine producing neurons were doing. How were they behaving? And he did experiments in the early 90s, recording from dopamine neurons in awake behaving monkeys. And he would, this shows a monkey in an apparatus, and it's, I think it presses something and then raisins, I believe, or he probably did lots of different rewards, but raisins were delivered. And initially, at this top histogram, shows a spiking of dopamine neurons at a little bit after the reward, the R was occurred. And below this shows the individual spike traces of the neurons he recorded. Up above is a sum of these. Now, if he created a CS, a conditioned stimulus, which is a predictor of the reward, what happens to the dopamine signals is that their activity moves back in time to the occurrence of the predictor and generally ceases at the actual time of the reward. And then at the bottom trace, if the reward is eliminated, there's a depression in the activity of the dopamine cells. And in fact, shown here on the right, if another trigger labeled here an instruction occurs earlier than the conditioned stimulus, the activity moves backwards to that and ceases at the time of the actual reward. So this was very puzzling. But those of us who knew about TD algorithms, it was like, oh, that's what the TD error does. That's exactly what it does. And this is a sketch of, you know, a version of that. And I won't explain it, but you see that you get this signal moving back to earlier predictors of the reward, and the signal disappears. It's canceled out by the prediction, by the value at the time of the reward. Then if you leave the reward off, you get a depression. This offset of the value creates a negative going pulse. So this qualitatively is what Schultz seemed to be observing. And in fact, this led to what has been called the reward prediction error hypothesis. And this was in a science paper by Schultz, Peter Dayan, and Reed Montague. This idea is that the phasic activity of mesencephalic dopamine neurons signals the error between an old and a new estimate of expected future reward. In other words, the TD error. And so this is a hypothesis that has been influential in neuroscience, although it has generated a lot of activity, either showing that it's false or that it's correct. And dopamine signals come in lots of different varieties, so it's not all of them. But this has generated a lot of activity in neuroscience, and this TD error was it didn't exist when well, I should say the data that Schultz found did not exist when this TD error correction process was generated, mostly in Sutton's dissertation. Okay. Now, I mentioned collective learning briefly, that associative search network, the reinforcement signal was broadcast to a team. It's called a team because they're all getting the same reward signal, to a team of RL units. And with the right learning algorithm, these team members can learn what they should do in order to improve the magnitude of the reinforcement signal. Now, it's a very difficult problem because the activity of each neuron, and these are stochastic units, the activity is corrupted by the activity of all the other units. The reward is depending on all of them. And so it needs a lot of experience to isolate what your influence is on this reward signal. It's a very difficult signal in noise recognition problem. But with the right algorithm, this does work. And in fact, this is a trace of dopamine neuron axon arbors from, I forget the animal, but you can see this very broadly branching axonal arbor. And of course, this suggests this team idea might make some sense from a neuroscience point of view. Now, the other thing that we looked at was at a multi-layer network, a deep neural network, there's a key credit assignment problem, namely, that the error backpropagation algorithm addresses with backpropagating derivative information. But we were interested in treating this as a collective behavior of reinforcement learning units. And in fact, you can broadcast a reward signal to all of these units. And with the right learning rule, it will learn to do nonlinear transformations that improve the reward signal. And I wrote a paper with Michael Jordan called Gradient Following Without Backpropagation in Layered Networks. And so error backpropagation, many people do not regard it as being biologically plausible. And so an alternative is something like this that seems very plausible. But the problem is, I don't have that slide. It's very, very slow. And certainly compared to backprop, which is computing these gradients, whereas these reinforcement learning units are estimating the gradient in the face of enormous amounts of noise. That they can do it at all is remarkable, but it takes a very long time, a lot of experience. And so with deep networks these days, people use backprop and not this reinforcement, or others have proposed reinforcement learning like methods to train multi-layer networks. But, it does work. It's very slow, but maybe, it seems much more plausible from a neuroscience point of view. Okay, now there are other topics that I do not have time to talk about. I've mostly talked about model-free reinforcement learning. It's related to classical conditioning. The TD algorithm is very closely related to Pavlovian or classical conditioning. Instrumental conditioning, reinforcement learning, secondary reinforcement, the idea of using TD errors as reinforcement signals is related to what in animal learning is known as secondary reinforcement. So something that has been associated with a reinforcer can act as a reinforcer itself. Then there are model-based methods that have environment models where they can do trial and error vicariously using the model. And one can look at planning and reasoning, problem solving, working memory. A lot of issues that are very interesting can be looked at in terms of model-based reinforcement learning. Then there are a lot of better algorithms. There are improvements in policy gradient algorithms. Improving algorithms make them converge more stably. There's also multi-agent RL. Well, these team problems are instances of that, but one can go much farther than the simple team arrangement. And then other people have worked on what they call distributional RL, which is instead of just trying to estimate expected values, tries to estimate the whole distribution, which can be related to some neuroscience data and can also be used beneficially in applications. Then there are groups looking at what is called computational psychiatry, where these ideas can suggest theories of various ways in which the nervous system can misbehave. And so there is using these computational principles to look at psychiatric disorders. It's a very interesting field, I think. Then another important thing is safety. And I do want to go into this a little bit. So RL poses some dangers, some challenges. One is, what should the reward signal be? If you're building a system, what are you going to reward it for? If it's playing a game, it may be easy, win or lose and so on, or proving, or having a theorem that has a known correct label. But in other cases, uh, it's not easy to do this. And in the book, you may have seen by Nick Bostrom, um, on dangers of AI, he called this perverse instantiation. Be careful what you wish for, you just might get it. And in fact, Norbert Wiener, who was the originator of cybernetics, warned of this problem 50 or 60 years ago by relating it to the supernatural story of the monkey's paw. Uh, and he was not talking about reinforcement learning, he was just talking about optimization. But RL includes optimization. And he says if it grants you what you asked for, not what you should have asked for or what you intended. And we have in the lab, doing simulations of RL systems, and we've provided a particular reward function, and the system comes up with something we did not expect. Because when you make an optimization problem, you don't know a priori what the optimal solution is, and it could be something quite unexpected. And this is a problem, I think, certainly for agentic AI, where agents are fielded in the physical world, and if they're self-improving using reward signals, um, you don't know a priori what they're going to end up with. And so this is a key problem that, and many people have looked at how to deal with this. You'd like this consequence to be aligned with human objectives. And so the alignment problem is part of this too. But this is a very old problem. It's not just RL, or it's not just AI. Okay, let me just stop, conclude. Computational studies of RL are tightly intertwined. The RL work that we worked was tightly intertwined with artificial neural networks. Both originated as hypotheses about how brains function and learn, and their development has been coupled from the very beginning. And then this issue of RL and agentic AI, I think, is a key issue that one has to be concerned about. And then I just conclude that the computational power of deep RL, united with recent results about the brain's reward system, point to how a next round of advances may come about. And here's a picture of many of my students, not everyone, I couldn't fit them all in, but some of them you may know. There's Rich Sutton up in the upper left, next to Chuck Anderson, Satinder Singh, who's a AI leader at Google DeepMind. I should point out that the lower right are 3 students who are professors now, 4 actually. 3 of them are professors at UMass and took over the lab that I used to direct. And the short guy is George Canandaris, who's a professor at Brown. Um, so um, I have to say that without wonderful students, none of this would have been possible. So it's been an astounding. Oscar Simsek is at Bath, University of Bath in the UK, and doing a lot of interesting reinforcement learning work. Okay, I think that's it. So thank you very much, and that's the end.